Welcome to Whispered Tales, where we gently unravel the lives of history's most fascinating figures, one whisper at a time. In this video, we embark on a serene journey through the extraordinary life of Sir Isaac Newton, the man who revolutionized our understanding of the universe. Isaac Newton, born on January 4, 1643, in Woolsthorpe, England, is often hailed as one of the most influential scientists of all time. His groundbreaking work in mathematics, physics, and astronomy laid the foundation for many scientific advancements that followed. From his formulation of the laws of motion and universal gravitation to his development of calculus, Newton's contributions have had a profound and lasting impact on the scientific world. Join us as we explore the life of this remarkable figure, delving into his early years, his groundbreaking discoveries, and the legacy he left behind. So sit back, relax, and let the story of Isaac Newton unfold in the gentle whispers of history. Isaac Newton was born on January 4, 1643, in the small village of Woolsthorpe, England. His birth was fraught with difficulties, arriving prematurely and with little hope of survival. His father, also named Isaac Newton, had passed away just 3 months before his birth, leaving his mother, Hannah Ayscough, to raise him alone. Newton's early years were marked by solitude and hardship. When he was 3 years old, his mother remarried, and Newton was left in the care of his maternal grandmother as his mother moved away to start a new family. This separation from his mother had a profound impact on young Isaac, fostering a sense of abandonment that would stay with him throughout his life. Despite these early challenges, Newton exhibited a keen intellect and an insatiable curiosity about the world around him. He spent much of his childhood in relative isolation, finding solace in observing nature and experimenting with mechanical devices. He constructed sundials, water clocks, and even models of windmills, demonstrating an early fascination with how things worked. At the age of 12, Newton was sent to the King's School in Grantham, a significant turning point in his education. Initially, he struggled to adjust to the school's rigorous academic environment. His introverted nature and the emotional toll of his early life made it difficult for him to engage with his peers and teachers. However, Newton's innate curiosity and determination soon set him apart. He began to excel in subjects such as mathematics, physics, and astronomy, laying the groundwork for his future contributions to science. Newton's years at the King's School were transformative. His teachers recognized his exceptional talents and encouraged him to pursue further education. During this time, Newton lodged with the Clark family, whose apothecary shop provided him with access to a wide range of chemicals and scientific instruments. This environment further fueled his interest in experimental science. In 1661, Newton enrolled at Trinity College, Cambridge, where he was exposed to the works of renowned scientists such as Galileo, Kepler, and Descartes. At Cambridge, Newton was initially a mediocre student, focusing more on independent study than on his formal coursework. He immersed himself in the study of mathematics, physics, and astronomy, often working late into the night. It was during his time at Cambridge that Newton's brilliance began to truly shine. He developed an intense interest in mathematics and made significant strides in the field. He worked on the binomial theorem and began to develop the foundations of what would later become calculus. Newton's mathematical genius was evident in his ability to see patterns and relationships that others had overlooked. In 1665, the Great Plague forced Cambridge to close, and Newton returned to Woolsthorpe. This period, often referred to as his annus mirabilis or Year of Wonders, was one of the most productive times in Newton's life. Isolated from the distractions of university life, he made groundbreaking discoveries in calculus, optics, and the laws of motion and gravitation. Legend has it that it was during this time that Newton observed an apple falling from a tree, leading him to ponder the forces of gravity. While the story has been romanticized over the centuries, it underscores Newton's ability to derive profound insights from simple observations. Newton returned to Cambridge in 1667, where he was elected a Fellow of Trinity College. In 1669, at the young age of 26, he was appointed the Lucasian Professor of Mathematics, one of the most prestigious academic positions in the world. In this role, Newton continued his work on optics, developing theories that would later be published in his seminal work Optics. He also began to formalize his thoughts on the laws of motion and universal gravitation, which would culminate in the publication of his magnum opus, Philosophiae Naturalis Principia Mathematica, or the Principia, in 1687. Newton's early life and education were characterized by a relentless pursuit of knowledge and a deep-seated curiosity about the natural world. Despite the personal and social challenges he faced, his intellectual brilliance shone through, setting the stage for a lifetime of scientific discovery and innovation. Newton's ability to overcome adversity and his dedication to understanding the universe around him laid the foundation for his enduring legacy as one of history's greatest scientists. Isaac Newton's contributions to mathematics are profound and far-reaching, laying the groundwork for many areas of modern mathematics and science. His innovations in this field began during his time at Trinity College, Cambridge, and continued throughout his career. Newton's work in mathematics not only showcased his extraordinary intellect, but also provided essential tools and concepts that have influenced countless disciplines. One of Newton's earliest and most significant contributions to mathematics was his development of the binomial theorem. The binomial theorem provides a way to expand expressions that are raised to any power, offering a systematic approach to polynomial expansion. Newton generalized the binomial theorem to apply to any real number exponent, which was a considerable advancement over previous work that had been limited to positive integers. This work laid the foundation for more complex mathematical analysis and demonstrated Newton's ability to extend existing mathematical principles. However, Newton's most famous and groundbreaking mathematical achievement is his development of calculus. Independently of German mathematician Gottfried Wilhelm Leibniz, Newton formulated the principles of calculus, which he initially referred to as the method of flux ions. Calculus is a branch of mathematics that deals with the study of change and motion, providing tools to analyze rates of change, differentiation, and the accumulation of quantities, integration. Newton's approach to calculus was driven by his need to solve problems in physics and astronomy, such as the motion of planets and the behavior of objects under the influence of gravity. His development of calculus allowed him to describe the changing velocities and accelerations of these objects mathematically. Although Newton's work on calculus remained largely unpublished during his lifetime, it eventually had a profound impact on the scientific community once it became widely known. One of Newton's key contributions to calculus was his development of the concept of limits. Limits provide a rigorous foundation for the study of continuous change, allowing mathematicians to define derivatives and integrals precisely. Newton's understanding of limits enabled him to formulate the fundamental theorem of calculus, which establishes a relationship between differentiation and integration. This theorem is a cornerstone of modern calculus and underpins much of the work done in mathematical analysis today. Newton's contributions to calculus also included the development of power series. A power series is an infinite series of terms that are expressed as powers of a variable. Newton used power series to represent functions and solve equations that could not be solved using traditional algebraic methods. This approach allowed him to approximate complex functions and provided a powerful tool for mathematical analysis. In addition to his work on the binomial theorem and calculus, Newton made significant contributions to other areas of mathematics. He developed methods for solving polynomial equations, known as Newton's method, which is still widely used in numerical analysis today. Newton's method is an iterative technique that provides approximate solutions to equations, making it an invaluable tool for scientists and engineers. Newton also contributed to the study of geometry and algebra. He explored the properties of curves and surfaces, developing techniques for analyzing their shapes and behaviors. His work in algebra included the development of techniques for manipulating algebraic expressions and solving equations, further demonstrating his versatility as a mathematician. One of Newton's notable mathematical works is his book Arithmetica Universalis, which was published posthumously in 1707. This book compiled his work on algebra and number theory, providing a comprehensive overview of his mathematical achievements. Arithmetica Universalis showcased Newton's ability to synthesize and extend existing mathematical knowledge, solidifying his reputation as one of the greatest mathematicians of his time. Isaac Newton's mathematical innovations were not limited to theoretical work, they also had practical applications. His development of calculus and other mathematical tools allowed him to solve real-world problems in physics, engineering, and astronomy. Newton's ability to bridge the gap between pure mathematics and practical applications is a testament to his genius and his profound impact on both fields. In summary, Isaac Newton's contributions to mathematics are unparalleled. His development of the binomial theorem, calculus, and other mathematical techniques provided essential tools for understanding the natural world. Newton's work in mathematics laid the foundation for many scientific advancements and continues to influence modern mathematics and science. His ability to innovate and extend existing mathematical principles has cemented his legacy as one of the greatest mathematicians in history. The laws of motion. Isaac Newton's formulation of the three laws of motion represents one of the most significant contributions to the field of physics. These laws, first published in 1687 in his seminal work Philosophiae Naturalis Principia Mathematica, commonly known as the Principia, provide a comprehensive framework for understanding the relationship between a body and the forces acting upon it. Newton's laws of motion form the foundation of classical mechanics and have stood the test of time as essential principles in the study of physics. First law, the law of inertia. Newton's first law of motion, also known as the law of inertia, states: an object at rest will remain at rest, and an object in motion will continue in motion at a constant velocity unless acted upon by an external force. This law introduces the concept of inertia, which is the tendency of objects to resist changes in their state of motion. In other words, a body will not change its velocity, which includes both speed and direction, unless a force is applied to it. This was a revolutionary idea at the time, as it contradicted the Aristotelian belief that a force is necessary to keep an object in motion. Newton's first law laid the groundwork for understanding how forces affect the motion of objects. A classic example of the law of inertia is a hockey puck sliding on ice. If we ignore friction and air resistance, the puck will continue to glide across the ice indefinitely at a constant speed and in a straight line unless an external force, such as a player hitting it with a stick, acts upon it. This law applies to both objects at rest and objects in motion, emphasizing the inherent resistance to changes in motion. Second law, the law of acceleration. Newton's second law of motion provides a quantitative description of the changes that a force can produce in the motion of a body. It states, the acceleration of an object is directly proportional to the net force acting upon it and inversely proportional to its mass. This law is often summarized by the equation F equals ma, where F is the net force acting on an object, m is the mass of the object, and I is the acceleration produced. The second law explains how the velocity of an object changes when it is subjected to an external force. It establishes that the greater the force applied to an object, the greater its acceleration, and the greater the mass of the object, the less it will accelerate for a given force. For example, consider a car that is initially at rest. When the engine exerts a force on the car, it accelerates in the direction of the force. If the same force is applied to a truck with a much larger mass, the truck will accelerate less than the car. This law is crucial for calculating the motion of objects under various forces and is fundamental in engineering and physics. Third law, the law of action and reaction. Newton's third law of motion states, for every action, there is an equal and opposite reaction. This law highlights the reciprocal nature of forces. When one body exerts a force on another, the second body exerts a force of equal magnitude but in the opposite direction on the first body. This interaction of forces explains the mutual influences that bodies have on each other. A practical example of the third law is the act of walking. When you push against the ground with your feet, the ground pushes back with an equal and opposite force, propelling you forward. Similarly, when a rocket expels gas out of its engines, the expelled gas exerts an equal and opposite force on the rocket, causing it to accelerate upwards. This law is essential for understanding the interactions between objects and is widely applied in various fields of science and engineering. Applications and implications. Newton's laws of motion have far-reaching applications and implications across numerous fields. They not only explain everyday phenomena but also underpin much of modern engineering and technology. These laws are used to design and analyze the motion of vehicles, machinery, and structures, ensuring their stability and functionality. In astronomy, Newton's laws provided the basis for understanding the motion of celestial bodies. They allowed scientists to calculate the orbits of planets, moons, and comets with remarkable accuracy. The laws of motion also paved the way for the development of classical mechanics, a branch of physics that describes the motion of macroscopic objects and systems. Newton's formulation of the laws of motion marked a turning point in the history of science. It provided a unified framework that could be used to explain a wide range of physical phenomena, from the motion of falling apples to the orbits of planets. Newton's work demonstrated the power of mathematical principles in describing the natural world and set the stage for future advancements in physics. In summary, Newton's three laws of motion formed the cornerstone of classical mechanics. The first law introduces the concept of inertia. The second law provides a quantitative description of how forces affect motion, and the third law emphasizes the reciprocal nature of forces. These laws have had a profound impact on our understanding of the physical world and continue to be fundamental principles in the study of physics and engineering. Universal gravitation. Isaac Newton's law of universal gravitation is one of the most profound and influential discoveries in the history of science. This law, which describes the gravitational attraction between masses, provided a comprehensive explanation for the motion of celestial bodies and revolutionized our understanding of the universe. First published in 1687 in Newton's seminal work, Philosophiae Naturalis Principia Mathematica, commonly known as the Principia, the law of universal gravitation unified terrestrial and celestial mechanics under a single theoretical framework. The law of universal gravitation. Newton's law of universal gravitation states, every mass attracts every other mass with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. Mathematically, this can be expressed as equals 1, 2, 2, F equals G, R, 2, M, 1, M, 2, where F is the gravitational force between two masses. G is the gravitational constant. 1, M, 1, and 2, M, 2, are the masses of the two objects. R is the distance between the centers of the two masses. This equation indicates that the force of gravity increases with the mass of the objects and decreases with the square of the distance between them. The gravitational constant, G, is a proportionality factor that ensures the correct units and magnitude for the force. The apple and the moon. The inspiration for Newton's law of universal gravitation is famously attributed to the observation of an apple falling from a tree. Legend has it that Newton began to ponder the forces at play when he observed the apple fall, leading him to question whether the same force that caused the apple to fall to the ground also governed the motion of the moon and other celestial bodies. This line of thinking led Newton to propose that gravity is a universal force, acting not just on objects on Earth but throughout the cosmos. Newton realized that the force causing the apple to fall to the ground could be the same force that keeps the moon in orbit around the Earth. By applying his law of universal gravitation, he demonstrated that the gravitational force exerted by the Earth on the moon provides the centripetal force necessary to keep the moon in its orbit. This insight was groundbreaking, as it provided a unified explanation for both terrestrial and celestial phenomena. Gravitational constant and Cavendish experiment. The gravitational constant, G, is a fundamental quantity that determines the strength of the gravitational force. It was first measured by Henry Cavendish in 1798, more than a century after Newton's formulation of the law of universal gravitation. Cavendish used a torsion balance to measure the tiny gravitational attraction between two lead spheres, allowing him to calculate the value of G. His experiment not only confirmed Newton's law but also provided a precise value for the gravitational constant, which is approximately 6.674 times 1, 0, minus 11 n m 2 slash kg 2 6.674 by 10 minus 11 nm 2 slash kg 2. Implications for celestial mechanics. Newton's law of universal gravitation had profound implications for celestial mechanics, the study of the motions of celestial objects. By applying his law, Newton was able to explain the elliptical orbits of planets as described by Kepler's laws of planetary motion. Kepler had empirically determined that planets move in elliptical orbits with the Sun at one focus, but he could not explain why this was the case. Newton's law of gravitation provided the theoretical foundation for Kepler's observations, showing that the inverse square law of attraction leads to elliptical orbits. Newton's work also explained the phenomena of tides. The gravitational pull of the Moon and the Sun on the Earth's oceans causes the rise and fall of sea levels. By understanding the gravitational interactions between these bodies, Newton was able to explain the regular patterns of tides observed on Earth. Additionally, Newton's law of universal gravitation allowed astronomers to predict the motion of comets. Edmund Halley, a contemporary of Newton, used Newton's principles to calculate the orbit of the comet that now bears his name, Halley's Comet. Halley's prediction of the comet's return in 1758 was confirmed, further validating Newton's theory. Universal gravitation and the cosmos. Newton's law of universal gravitation extended beyond the solar system, offering insights into the behavior of stars, galaxies, and the structure of the universe itself. The same gravitational principles that govern the motion of planets also apply to stars within galaxies and galaxies within clusters. Newton's work laid the foundation for the field of astrophysics, allowing scientists to explore the dynamics of the cosmos on both small and large scales. One of the most significant implications of Newton's law is the concept of gravitational binding. This concept explains how objects are held together by gravitational forces, whether they are planets orbiting a star, stars orbiting within a galaxy, or galaxies interacting within a cluster. Gravitational binding is a key principle in understanding the formation and evolution of cosmic structures. Newton's legacy. Isaac Newton's law of universal gravitation remains a cornerstone of classical physics. It provided a unified framework for understanding the forces that govern the motion of objects both on Earth and in the heavens. Newton's insight that the same force responsible for the fall of an apple also governs the motion of celestial bodies was a revolutionary idea that transformed our understanding of the universe. While later advancements, such as Einstein's theory of general relativity, have expanded our understanding of gravity, Newton's law of universal gravitation remains an essential approximation for most practical purposes. It continues to be taught as a fundamental principle in physics education and is used in a wide range of scientific and engineering applications. In summary, Newton's law of universal gravitation unified the understanding of gravitational forces, provided a comprehensive explanation for the motion of celestial bodies, and laid the groundwork for modern astrophysics. Newton's genius in recognizing the universal nature of gravity has left an enduring legacy, cementing his place as one of the greatest scientists in history. Later years and legacy. In the later years of his life, Isaac Newton continued to be an influential figure in both scientific and public spheres. His work during this period was marked by significant achievements and contributions, as well as by his growing reputation as one of the greatest minds in history. Newton's legacy extends far beyond his scientific discoveries, impacting various fields and setting the stage for future advancements in science and mathematics. Public service and the Royal Mint. In 1696, Newton was appointed Warden of the Royal Mint, a position that marked a significant shift from his academic pursuits to public service. 3 years later, he was promoted to Master of the Mint, a role he held until his death. Newton took his responsibilities at the Mint very seriously, applying his analytical skills to improve the accuracy and reliability of the nation's currency. His efforts included combating widespread counterfeiting, which was a major issue in England at the time. Newton implemented rigorous measures to standardize the coinage and ensure its integrity. His work at the Royal Mint demonstrated his meticulous attention to detail and his commitment to public service. Despite the administrative nature of his role, Newton approached it with the same dedication and thoroughness that characterized his scientific work. His tenure at the Mint was highly successful, and he is credited with stabilizing the British currency, which had been plagued by inconsistencies and fraud. Leadership of the Royal Society. In 1703, Newton was elected President of the Royal Society, a prestigious institution dedicated to the advancement of scientific knowledge. He held this position for 24 years, until his death in 1727. As president, Newton played a crucial role in promoting scientific research and fostering collaboration among scientists. Under his leadership, the Royal Society became a leading center for scientific inquiry and innovation. Newton's presidency was marked by his strong support for scientific exploration and his efforts to maintain high standards of research and publication. He oversaw the publication of numerous scientific papers and encouraged the exchange of ideas among the members of the society. Newton's influence extended beyond the Royal Society as he corresponded with scientists across Europe, further establishing his reputation as a leading intellectual figure of his time. Religious and alchemical interests. In addition to his scientific and public service roles, Newton devoted considerable time to religious and alchemical studies. He was deeply interested in theology and spent many years studying biblical texts and seeking to reconcile his scientific discoveries with his religious beliefs. Newton wrote extensively on theological subjects, including interpretations of biblical prophecies and the nature of the divine. Newton's interest in alchemy was equally intense. Alchemy, the precursor to modern chemistry, was a field that sought to transform base metals into noble ones and discover the elixir of life. Although much of alchemy was based on mystical and speculative ideas, Newton approached it with a rigorous experimental mindset. He conducted numerous alchemical experiments and wrote extensively on the subject, although much of his work in this area remained unpublished during his lifetime. Newton's religious and alchemical studies reflect his quest for a deeper understanding of the natural and spiritual worlds. These interests, while not as widely recognized as his scientific achievements, were integral to his intellectual pursuits and reveal the breadth of his curiosity and dedication to exploring all aspects of knowledge. Final years and death. In his final years, Newton continued to be active in his various roles, although he gradually withdrew from public life due to declining health. Despite his physical ailments, he remained mentally sharp and continued to correspond with fellow scientists and scholars. Newton's contributions to science, mathematics, and public service had firmly established his legacy, and he was widely regarded as one of the greatest thinkers of his time. Isaac Newton passed away on March 31, 1727, at the age of 84. His death marked the end of an era in scientific history, but his influence endured. Newton was buried with great honor in Westminster Abbey, a testament to his immense contributions to society. His funeral was attended by prominent figures of the time, reflecting the widespread admiration and respect he had earned throughout his life. Newton's legacy. Isaac Newton's legacy is vast and enduring. His discoveries in mathematics, physics, and optics laid the foundation for many of the scientific advancements that followed. Newton's laws of motion and universal gravitation remain fundamental principles in the study of physics, and his development of calculus provided essential tools for mathematical analysis and scientific inquiry. Newton's approach to scientific investigation, characterized by meticulous experimentation and mathematical rigor, set new standards for research and established the scientific method as a cornerstone of modern science. His work inspired generations of scientists and thinkers, paving the way for the Age of Enlightenment and the subsequent scientific revolution. In addition to his scientific achievements, Newton's contributions to public service and his leadership of the Royal Society helped to promote the advancement of knowledge and foster a culture of intellectual curiosity and collaboration. His efforts to improve the nation's currency and his role in combating counterfeiting demonstrated his commitment to applying his skills for the public good. Newton's religious and alchemical studies, while less well known, reveal the depth of his intellectual pursuits and his desire to explore all facets of existence. These interests highlight Newton's multifaceted character and his unwavering quest for understanding. Newton's impact extends beyond the realm of science. His life and work have been the subject of numerous biographies, academic studies, and cultural references. He is often portrayed as the quintessential genius whose insights transformed our understanding of the natural world. Newton's name has become synonymous with scientific excellence and intellectual achievement. In summary, Isaac Newton's later years were marked by continued contributions to science, public service, and intellectual exploration. His legacy is a testament to his extraordinary intellect, dedication, and curiosity. Newton's work continues to inspire and inform, solidifying his place as one of the greatest minds in history. As we conclude our serene journey through the extraordinary life of Sir Isaac Newton, we are reminded of the profound impact that one individual can have on our understanding of the universe. Newton's unparalleled contributions to mathematics, physics, and optics have left an indelible mark on the world of science, and his legacy continues to inspire and inform countless generations of scientists, engineers, and thinkers. From his humble beginnings in Woolsthorpe to his groundbreaking discoveries at Cambridge, Newton's relentless curiosity and dedication to uncovering the mysteries of the natural world set him apart as one of history's greatest minds. His formulation of the laws of motion and universal gravitation revolutionized our understanding of the physical world, providing a unified framework that explained both terrestrial and celestial phenomena. Newton's work in optics, particularly his experiments with prisms and his development of the reflecting telescope, transformed our knowledge of light and color, laying the foundation for modern optics. Newton's influence extended beyond the realm of pure science. His roles as warden and master of the Royal Mint demonstrated his commitment to public service and his meticulous approach to ensuring the integrity of the nation's currency. As president of the Royal Society, Newton fostered a spirit of collaboration and scientific inquiry that propelled the advancement of knowledge and innovation. Despite his immense achievements, Newton remained a humble and introspective individual, dedicating his life to the pursuit of truth and understanding. His religious and alchemical studies, while less recognized, reflect his quest to explore all facets of existence and to reconcile his scientific discoveries with his spiritual beliefs. Isaac Newton's legacy is not just one of scientific brilliance, but also of perseverance, curiosity, and a profound dedication to uncovering the secrets of the universe. His ability to blend empirical observation with mathematical precision set a new standard for scientific inquiry and paved the way for future advancements in science and mathematics. As we reflect on the life of Isaac Newton, we are reminded of the boundless potential of the human mind and the transformative power of knowledge. Newton's story is a testament to the enduring impact that one individual can have on the world, and his legacy serves as an inspiration for us all to continue exploring, questioning and seeking out the mysteries that lie beyond. Thank you for joining us on this whispered journey through the life of Sir Isaac Newton. If you enjoyed this video, please like, comment, and subscribe to Whispered Tales for more captivating stories from the annals of history. Let Newton's story inspire you to explore the wonders of the natural world and to seek out the mysteries that lie beyond. Until next time, sweet dreams and good night.